start with the questions right away. And question number one is a very good question. In which direction did the Big Bang happen? So, this is a question I believe that all kids would have, all new students of physics would have about the Big Bang theory. I'm sure I must have had this question when I was a kid. And this is a question that no teacher essentially answers. They discourage you from asking questions. And that's why this question remains with us for the remainder of our lives. So, in what direction did the Big Bang happen? So let's understand what this Big Bang was. So, according to the best theory of the universe that we have, the so called Big Bang theory, the universe began as an extremely compact and extremely small point, just one small point, infinitesimally small. All the mass and energy of the universe was concentrated in that point, and it expanded from that. So it's not an explosion, it's an expansion. What is the difference between the two? An explosion is something that happens in one place, like a cracker bursting or a grenade blast. So it is something that happens in one place and it ejects material in all directions. So if the Big Bang was an explosion of the universe, you would find bits and pieces of the universe being thrown out in different directions. That's not the case. The universe is just one, it's one single entity. So it was a very rapid expansion, an incredibly, humongously, ridiculously rapid expansion. So that's what happened. So that was the Big Bang. And the universe expanded superluminally, which means it expanded at faster than the speed of light. So that's why it looks like like an explosion. That's why this colloquial term Big Bang has been used for it. So because of the way the universe expanded, it means that every single place, every single location in the universe was once concentrated in that small little singularity or near singularity, which means that the Big Bang happened everywhere. Everything was part of the Big Bang. Where I am sitting right now, it was part of that initial extremely condensed, extremely small state in which the universe existed. And wherever you're sitting right now, that was also part of it. What this means is that it is not incorrect in any way to say that the Big Bang happened everywhere. All of the space time that we have around us today, that we are inside, was part of this initial expansion of the universe. So the Big Bang basically was the entire universe. And therefore, it happened at all places at the same time. It happened here, it happened where you are, it happened where Jupiter is, it happened at the Andromeda galaxy, it happened in the farthest galaxy supercluster that we can observe, etc. Everything was part of it. So there is no actual direction. Everything was inside that little tiny, infinitesimally small point that was the uh, very early universe. So that's how it is. So I hope that answers your question. It clarifies your question to some extent, hopefully. Avinash again asks the same, a different question. Why did the Big Bang take place? That's another very good question. So the best theory, like I said, that we have of the universe is the so-called Big Bang theory. Now, what does this theory say? First of all, what is this theory? This theory is a model of the history of the universe. This is the best theory that we have, and it's a model of the history of our universe after the Big Bang occurred. It is not a theory of the creation of the universe. That's what we have to understand. There's a big difference. The Big Bang theory is not a theory of the creation of the universe, it is a model of the history of the universe after the Big Bang took place and after the very early period of the universe's history, which we don't really understand very well. So, around 10 raised to so basically, the universe had a birthday. The universe, there was a point in time, so to say, before which there was no yesterday in the universe. So the universe emerged at a certain time, at a certain time, you can say that, yeah. But before that, there was no time. So the universe had a birthday, and everything proceeds further in a certain direction of time from that point onwards. So when the universe was about 10 raised to minus 36 seconds old, it was about the size of of a tennis ball or cricket ball or an apple. So we begin to understand the Big Bang theory essentially begins to understand the universe from that point onwards. Because before that, you had grand unification, which we don't quite understand. So before that point, basically, all four forces that we know of in nature, the strong nuclear force, the weak nuclear force, electromagnetism, and gravitation, these were all of equal strengths. Gravity's role was much more prominent at that time, right? It was as strong as the other forces, and afterwards the forces decouple into the in become similar to what we experience today. So our understanding of the early universe proceeds forward from that point onwards, from 10 raised to minus 36 seconds onwards, and it's an approximate understanding of how things occurred. So basically, the Big Bang theory is a model of what happened from that point onwards. It doesn't seek to explain, it is not able to explain what caused the initial expansion itself. So you go and ask any scientist, any theoretical physicist in the world, they will not be able to answer why did the Big Bang take place, what caused it, what triggered the initial expansion of the universe, what triggered the creation of the universe. We don't know. So these are the limitations that we currently have in our understanding of the universe, and in our understanding of science itself, of the laws of nature itself. So there's a great deal to understand. There's a great deal that we don't know. So that's what I keep emphasizing, that there is so much to. That's why physics, and theoretical physics and physical cosmology and astrophysics, that's why it's so interesting, it's so fascinating, because there is so much still left to understand, so much still left to discover. The history of the very early universe is an especially fascinating topic, because it basically talks about grand unification, which is the so-called holy grail of physics, the unification of the four forces of nature, and any others, if any others do exist. So basically, that's your answer. We do not know what triggered the Big Bang, what laws or what forces or what it was that triggered this event. We don't know. We only understand what happened after a certain point in the very early history of the universe, and that too, it's an approximate understanding. There are still many data points that we don't have, and many things we still don't understand. But it is the best theory that we have as of now, and it does explain a lot about the universe, and we do have a lot of evidence that supports this theory. So that's your answer, sir. Avinash again asks, what is it like inside a black hole? So what we understand about black holes comes from the theory of general relativity. And this theory says that when you take a mass, any mass, and you compress it further and further, the effect it has on space-time becomes more and more acute. So if space-time is a sheet and a ball of mass produces this distortion in the field in the sheet, then the more condensed a mass is, the more dense a mass is, the greater it's going to stretch the fabric of space-time. And if you compress a mass sufficiently enough so that it becomes equal to or less than its so-called Schwarzschild radius, then it basically produces an infinite amount of warping of this fabric of space-time, and that's what we call a black hole. So the equations of general relativity, Einstein's equations, they produce what's called a singularity, which means it's division by zero. It doesn't mean that there's an actual infinite density in there. It actually means that our theory isn't able to handle that specific condition. It means our theory isn't accurate enough. It shows up the limitations of the theory of general relativity. It tells you that we need to be able to formulate a better theory. We need to formulate a better theory, one that takes into account the quantum domain of the universe. So we basically need to find a way to reconcile quantum mechanics, quantum field theory, and general relativity, which is something we haven't achieved thus far. Because if you try to quantize gravity, it doesn't work. It blows up. It breaks down. You cannot have space. I mean, you cannot have Quantum field theory doesn't work in curved space-time, etc. So these are the problems that theoretical physicists are grappling with. So essentially, what I'm trying to say in so many words is we don't know what's inside a black hole. A black hole is something it's a region of space-time that's cut off completely from outside orbit, from outside observers. The boundary is what's called the event horizon, and there is no way of knowing what's inside because everything that goes inside never comes out, except in the form of thermal radiation, the so-called Hawking radiation, which doesn't tell you anything about what's really inside the the, the black hole. So what's inside a black hole, we don't know. There could be, well, there are speculations. A black hole could possibly be a bag of single dimensional strings, perhaps. It could be something that contains just radiation, photons. Maybe it contains just pure mass. That's another speculation or possibility. Some people say that a supermassive black hole could, or any black hole, could essentially be a pathway to a different universe. It could end on the other side in a white hole and bring you out in a different universe in which time flows backwards. And then it's also a possibility that supermassive black holes may contain entire universes inside them. So these are speculations, but we have no way of knowing. First of all, because we don't have access to a black hole on which we can do experiments, because you know what black holes do, they suck everything in. So we don't have access to a black hole in a laboratory. We don't have any black hole that anywhere nearby us that we can observe and get a get better idea of. And the theoretical framework that we have isn't able to explain or answer these questions of what is the internal structure of a black hole. We know that black holes have mass, they have charge, they have angular momentum, and basically these are the three things that characterize the properties of a black hole. We don't know much beyond that. So there is a great deal of research happening into this matter. But as of today, this is another example of the limitations of our understanding of nature. We don't know what is the internal structure of a black hole. We don't know what's inside. We don't know what's beyond. So it's a great question, and these are the questions that drive physics forward.